So now we're going to talk about the second line of, or I'm sorry, we're going to talk about some of the chemical ways that innate immunity is going to be able to uh, protect you. So there are, on the skin, we're going to use mechanical means like we talked about, but we're also going to talk about things like fatty acids and beta defensins and calcitonin. In the gut, again, defensins, but here alpha defensins or cryptins. Reg3, um, which goes after lectins, and again, calcitonin. In the lungs, alpha defensin again. So in the gut and lungs, alpha defensins, and in the eyes, nose, and oral cavities, beta defensins, and um, um, in the eyes, nose, and oral cavity, you've got saliva and tears. You've got cilia. You've got mucus, um, and contained in those tears and saliva, we've got enzymes like uh, like lysozyme. In the gut, we've got a low pH as well as enzymes like pepsin. And in the lungs, we've got surfactants that cause these things to go into solution. So then more and more is being learned now about how the microbiota are also protecting you against invaders. So besides the mechanical barrier on your skin of the dead epithelial layer, you've also got some lipids. So that's going to create a watertight layer in the just above the basal lamina in that stratum granulosum. So so that those lipids are secreted by cells inside of um, the epithelial layer, or I'm sorry, uh, inside of the dermis, the the dermis that is just above the basal layer. Then in your lungs, you've got ciliated epithelia that are going to create a flow out of your lungs of the mucus, as well as goblet cells that are producing um, some of those defensins and Reg3 and ficulin and um, some of these antimicrobial proteins and peptides. And then in the gut, you've got the Paneth cells that are doing the same sort of thing. They're producing defensins and Reg3. Um, and you've also got macrophages that are there in the Peyer's patches being sentinel. So, oh, and you've also got goblet cells that are producing mucins and uh, creating a mucus layer that is protecting the cells from the pepsin, but also preventing microbes from getting on those cells. So you got in your in your lungs, you've got the epithelia that are ciliated, and then the mucus, and the mucus is constantly trapping all of these microbes and keeping them from getting into the epithelia. And your cilia is constantly beating to create a mucus elevator up out of your lungs until your trachea meets your esophagus, where you'll just swallow it into the alimentary canal and deal with it with pepsin. So it's important that they go into solution, and that's why we produce surfactants there in the lung. Um, if you have cystic fibrosis, on the other hand, those cilia are unable to beat the mucus out because of the low water content of the mucus, and that's due to cystic fibrosis is caused by a chloride channel. An ABC chloride channel has either not gotten to the surface, that's the most common mutation, or is inoperative when it gets to the surface. And so with less chloride in the extracellular space, you've got less osmotic flow of water into the extracellular space, and so that mucus just gets too thick, and the cilia can't move it up through the mucus elevator, and so those bacteria are now staying in the lung longer and are able to cause lung infection. Um, so normally, what you've got on your epithelial layer is the bacteria are on the outside, right? It's only once you have an insult to the physical barrier that that these bacteria get introduced into the tissue. So part of wound healing is that antimicrobial proteins and peptides and phagocytic cells, such as macrophages and dendritic cells, will move into the area. So hopefully these antimicrobial proteins will destroy the bacteria, or they will be phagocytized by these cells, or maybe complement will destroy the invading organism. Um, the swallowing of the bacteria by these macrophages and dendritic cells releases cytokines that cause the microvasculature in the tissue to become more permeable, more leaky, and so cells will move out into the tissue. And once those cells move out into the tissue, they can assist. So now you've got granulocytes showing up, more macrophages, natural killer cells showing up, and then this is a two-way street, because once they've engulfed those bacteria, then they will move through the lymph system into the secondary um, uh, immuno organs, like the lymph nodes. And there they will activate the adaptive immune system. Blood clotting also helps limit the spread of infection, and the clot itself releases cytokines like D-dimer to induce uh, chemotaxis and the innate immune system moving toward the blood clot. And then finally, the cells that were activated there in the lymph nodes by those antigen-presenting cells that had phagocytized the bacteria are now going to show up. And if they are B cells, they're going to be giving off, because they will mature into plasma cells, and those plasma cells are secreting um, specific antibodies to the pathogen, as well as T cells showing up and maybe activating the macrophages to be more aggressive. And then maybe there'll be some cytotoxic T cells showing up if they were activated by MHC class 1, which is even possible in the case of bacteria. I know I told you that it was viruses, but it's even possible in the case of bacteria, and we'll talk more about that in a much later chapter. I think that's chapter 8. So some of the chemicals that are produced, like lysozyme, are really important for breaking down the proteoglycan layers of the bacteria. So you've got two kinds of bacteria, essentially, the gram-positive and gram-negative, at least in COSA. Those are the two major kinds. And what the lysozyme does is it is able to it's an enzyme that is able to cut through this peptidoglycan layer, whether that is a gram-positive bacteria or a gram-negative bacteria. The lysozyme is able to cut through. In the case of LPS is able to fight this off a little bit, but lysozyme is able to cut the peptidoglycan layer in both gram-positive and gram-negative bacteria. And this is going to be important because we need to get to that cell wall is protecting the lipid bilayer, and the lipid bilayer is the point of attack for things like complement as well as some of the defensins and stuff like that. So let's talk a little bit about defensins. Defensins are proteins, and they are amphipathic, which means that they like both lipids and water. So they have a polar side and a non-polar side. And so they'll insert themselves into the lipid bilayer, and because they are attracted to each other, they can cause a pore to form they just disrupt the lipid bilayer because they are amphipathic molecules, much the same as some detergents do. They're much bigger than a detergent, but they're doing it in a similar way. So defensins are almost every one of them is produced by the genome in a pro form. Which means that they have to get activated by proteolysis. So only once they are cut can they work, because excuse me, the part that gets cut off is covering up part of the amphipathic nature of them, and it's that being both polar and non-polar that makes them work. So if that non-polar region is there in the center of the protein, then it's not going to be able to insert itself into the membrane. So they get produced as inactive proteins, and then get activated by proteolysis in the site of the wound. So the next thing we're going to talk about is complement. So I'll just talk just really briefly about complement. So the way that complement works is first pattern recognition triggers it. Then there's a protein cascade. These proteins, one of them is cut, that causes it to become an enzyme that cuts the next one, that causes it to be an enzyme that cuts the next one. And so this proteolysis cascade, and the result of that is pieces of it cause inflammation, pieces of it cause the bacteria to be phagocytized, and pieces of it are able to cause holes in the membrane, called the membrane attack complex. So there's quite a few proteins involved in the complement system. So just a brief overview. We've got multiple pathways. We've got the lectin pathway, the classical pathway, and the alternative pathway. Although the alternative pathway is the oldest pathway, the classical pathway was discovered first, and that's why the alternative pathway is called the alternative pathway. So in both the lectin and classical pathway, you've got these big complexes that are able to generate a C3 convertase. So let's talk about the lectin pathway first. You either got phycolin or MBL, which is carrying proteolytic enzymes with it that will cut C4 or C2. In the classical pathway, you've got C1, which again is able to cut C4 and C2. And then in the alternative pathway, sometimes C3 gets cut, undergoes hydrolysis on its own, and that spontaneous hydrolysis activates the pathway. So in the next video, we'll talk about all of the details of that, but the downstream of that is that we cause inflammation, we cause opsonization, and we cause the membrane attack complex.